All right, let's go ahead and talk about dynamic equilibrium. And to understand dynamic equilibrium, we first need to understand that many chemical reactions are reversible. In other words, if we have two reactants and the reactants start to react, as they turn into products, the products then start to react with each other to turn back into reactants. And so if you take a look at the top, you'll see we have dynamic equilibrium, the words there, and it's going back and forth. And so these reversible reactions, what ends up happening is they go back and forth, and they continue to go back and forth. Now, a double arrow indicates that a chemical reaction is reversible. Typically, we would, in the past, write a reactant, we would write a yield arrow, which shows the arrow going in one direction to the products. But if a reaction is reversible, we have a double arrow going both ways. Notice how they're half arrows, showing that it can go backwards. Now, when we are talking about equilibrium and what equilibrium is, something that we need to keep in mind is that when equilibrium is achieved, the amount of product and both product and reactant are present. And so once equilibrium is achieved, we have both product and reactant. Now, dynamic equilibrium is achieved when the amount of reactant that is turning into product is equal to the amount of product turning into reactant. And I really want to make sure that we understand what that means. So the amount going forward, the amount of reactant turning into product is equal to the amount of product turning into reactant. What it does not mean, that the amount of product and the amount of reactant is the same. In fact, we'll see that most situations it's not the same. We might have a lot more product in the end, or we might have a lot more reactant in the end. But what is the same is the amount going forward and the amount going backwards. That's what is the same. So the concentrations in the end are not necessarily the same. In fact, they usually are not, but it's the amount going forward and the amount going backwards. Now, when equilibrium is achieved, the concentration of product and reactants are constant. All right, now because we can now have both products and reactants, we need a way to describe the relative amount of product and the relative amount of reactant. Each chemical equation or each chemical reaction will end up with a different amount of product and reactant in the end. And so what we can do is we can assign what is called a K value to each chemical reaction. And what the K value tells us, it pretty much tells us the ratio of product to reactant. It tells us how much product there is and how much reactant there is. Now, if we're dealing with aqueous solutions, it tells us that we think about it in terms of concentration, in terms of molarity. However, if we're dealing with gases, we think about it in terms of partial pressures. And so equilibrium, and this occurs at, when we assign a K value, we're assigning it at a certain temperature, because as you change the temperature, the K value actually changes. So this is the expression for K. This is the equation for calculating K. Now, before this scares you, we will never ever have to calculate K. You will never have to sit here and calculate, plug in those variables and all that. You do need to understand this setup though. You do need to understand how it is. And there's a couple things I want to point out. First off, notice how it's products divided by reactants. It's the ratio of product to reactant. And notice how it's the products, the concentration of the products raised to the power of their coefficient multiplied together, divided by the concentration of the reactants raised to the power of their coefficient from the balanced chemical equation multiplied together. And so the product molar concentration, or partial pressure for dealing with gases, is always going to be in the numerator. So essentially the products are always in the numerator. The reactants will always be in the denominator. And each concentration or partial pressure is raised to the power of their coefficient in the balanced chemical equation. Now, what's nice about this is we're not going to have to calculate anything, but if we're given a certain K value, we can actually determine, based off the K value, if we're going to have more product or if we're going to have more reactant. So we are going to be asked to do that. So something else to keep in mind is that in a chemical reaction, If there are solids or liquids, solids and liquids are not part of the expression, and that's going to be very important later. And this expression has no units, so there's no units to the K value, all right? So we don't include solids or liquids, and there's no units to the K value. Now, this is where we're going to talk about what we can do with this K value. So if K is greater than 1, what does that mean in terms of reactants and products? Which one do we have more of? Well, how do we get a value greater than 1 in an equation like this? We need a larger numerator. So again, the numerator is the products, it's products over reactants. If a K is greater than 1, that means we have more products. And so that means the formation of products is favored. And so if we have, again, a K value greater than 1, that means products are favored. Now what about a K value that's less than 1? Well, again, looking at the expression there, how do we get K value that's less than 1? Well, we would need more denominator. And again, reactants are in the denominator, so that means that reactants would be favored if K value is less than 1. Now, if K value is equal to 1, that means that reactants and products are equally favored. And again, this is kind of a rare situation. It's not, doesn't happen all the time. And so they're about the same if the K value is equal to 1. All right, so let's go ahead and take a look at this graph. Let's explain the graph and let's talk about which one is favored. Take a look at time 0. Notice how the concentration of product is 0. There's 0 product at time 0. And we have only reactant. But as time starts, the reactants start to react together to turn into product. When that happens, there's a decrease in reactants and there's an increase in product. But again, as for reversible reactions, as products are being formed, those products can then start reacting with each other to turn back into reactants. And you can see that as the reactants go down, the concentration of reaction go down, and as the concentration of product go up, what ends up happening is it flattens out. And so eventually what will happen is the curve will flatten out, and the exact point in which it flattens out is the point that equilibrium is achieved. So again, equilibrium is achieved the moment the curve goes flat. Now, notice how it stays flat and keeps going. That's because the concentration of reactant and product are unchanging at equilibrium. That does not mean that there's not a reaction occurring. What it means is that their concentrations are unchanging. However, there are reactants going to becoming products, and there are products becoming reactant. It's just that the amounts are equal. So yes, it's unchanging, but there's still a reaction happening, and the amount going forward is equal to the amount going backwards, which is why it's unchanging. It's kind of like if I give you $1 and you give me $1, our net worth is not changing. Yes, you get my dollar and I get your dollar. There's something happening, but our overall net worth is not changing. So in this situation, products are favored because we end up with more product, meaning that we have a K value greater than 1. In this situation, because we end up with more reactant, that means that reactants are favored. And again, because reactants are on the bottom, that means we have a K that's less than 1. And that's it. So we're going to apply this concept to other chemistry concepts. And as we do that, things will start to come together a little bit more. I know that there's a lot of concepts in this particular concept that is kind of hard to grasp initially. But again, as we start doing practice problems, as we start talking about it more in the context of other chemistry concepts, it starts to come together and things will be great. So come to class with questions, come to class ready to practice this and apply it, and have a great day.